All right, chapter 15. We begin on the Laplace transform. So we're going to be doing in the next several chapters two different transforms, both extremely important, Laplace and then Fourier. So beginning with Laplace, math intensive, so let's be careful and get to it. We'll start with just a definition. And it's a transform. So this is not the same as a transfer function, which we've introduced and studied under Bode plots and this sort of thing. This is a transform. So what we're more likely to be doing is we're going to be working with transforming a time function. So this could be a driving function or a forcing function that will be used in a network that is described by a transfer function. All right, so it allows us to get time functions into the S domain. That's what we're after here. Okay? And the definition is this. It's a definition. So it's an integral function of the function itself over time multiplied by e to the minus st. Okay? And remember, we had in the last chapter, we had e was j omega. S was j omega. Okay, so now we're going to add to that a real portion, and we're going to say S is sigma plus j omega. Okay, so this is, again, a definition of the transfer function. Notice it starts at 0. This is called the one-sided transfer function for obvious reasons. Now, this goes 0 to infinity, and you say, well, what about all the negative side? What if I go from minus infinity to plus infinity? So this first equation, though, assumes that this function is time greater than 0. Okay? And f of t is constrained by that. Right? Constrained by that idea. Okay, but sometimes f of t has, right, some elements of t less than 0. All right? In that case, we can always apply, right, the unit step function, right, u of t, right, which remember is equal to, it's equal to 1 for t greater than or equal to 0, and the step function is 0 when t is less than 0. Okay? So it's nice to have that. That's what we've got. And this would be the full Laplace transform called the two-sided transform. Now, so few problems, none that we're going to encounter in electrical engineering, the functions of time we're interested can be determined from a starting point. So we'll say right up, in this course, we're not going to explore the two-sided transform. Should we need it? We'll just use tables. In fact, over time, you're going to learn to rely on tables a lot, because this is going to be math-intensive stuff, pretty math-intensive stuff. Okay, so there are two related things that need to be added here before we move into a lot of the properties of the Laplace transform. And the first one is convergence. I just want to say that every f of t doesn't necessarily have a Laplace transform. In other words, if I look at it, so for every f of t, there's not always an L of t. Okay, and the thing that can determine this or make it not possible to have a transform is if it doesn't converge. You have to remember that the definition here included what? An integral from 0 to infinity. Okay, so if whatever I've got going on in here, dt, doesn't converge at infinity, I'm not going to have, I don't have a viable transform. I don't have a useful transform at all. All right? So here is a picture of that, or at least a definition of that. And what's going on is we know, remember the S has two parts, right? The S is sigma plus j omega, right? So when that gets plugged in to our Laplace definition, we end up with the term e to the sigma t and e to the j omega t. Okay, but we know this term, the magnitude of this term, heads to 1, right, for any value of t, right? So what does that mean? That means convergence comes back to this term. If we're going to have convergence, the success or failure of that comes back to that term. And that's what's being expressed here. Okay? And for this to be the case, this needs to be real. Or actually, we're just talking about the real part of it. So what that means is this needs to be constant, right? So it's often expressed as a constant. And we end up with a region of convergence. So here's the point of it, a picture of the region of convergence. And you can see it's really built around, this is picking a point. This is a delta axis. So this just picks a point where as long as sigma is greater than some constant value, right, that implies that this is going to converge. You can easily see negative values, e to the minus delta, that's ending up e to the positive. So that's an exponential that's going to take off. So we're not going to discuss this a whole lot, except it's important to say that not everything has a Laplace transform. Okay, the second thing I want to mention is the inverse. Every time you transform something, it's nice to know you can get back to the original. And so something like this is needed, an inverse transform. Okay, you may remember when you were doing simultaneous equations and you learned the matrix method of solution, one of the things you needed to do was find the inverse of a matrix. It's the only way back. All right, so this is just that expression. If I have an f of s, I want to know I have an inverse transform. These things can be a lot of work. Here is that idea, okay? And pretty much, we're not going to get tangled up. I guess what I want to say here is, more than pretty much, we're not going to get entangled with finding inverses. We're going to learn to use the tables. Because just like the two-sided Laplace transforms, the math here can get pretty intense, and it's not necessary for us. In EE, we know what the basic set of math functions are that we're using and reusing, and how they occur, how they present themselves in real life. And so that stuff has been well tabulated in both the forward and the reverse direction. And we'll probably rely on those, though we are going to take the trouble to find a few mathematically Laplace transforms here, just to get familiar and comfortable with the idea. And in all our circuits, our circuits of interest, we're not too worried about convergence, because the ones that we are going to be working with, not just because we're in the text, but the ones that generally happen for us in real life, do have these bounds to them like this, and we have the tables to do the inverses. So we're generally in pretty good shape there. Okay, I want to look at a couple of problems. This just meaning we can go back and forth. We want to be able to go back and forth. I want to do a couple of problems, and I wanted to remind you of this identity, right? That you may remember Euler's identity. So it's something that relates sines and cosines with the exponential, right? The sines and the cosines related to the exponential. We need to do that because we now have a Laplace transform, which is going to invoke exponentials, right? E to the st, where s is complex number. But we know in real life, in electronics and electricity, we're interested in sines and cosines and time varying signals. So we need a way to deal with that. But let's begin. There are going to be a lot of properties of the Laplace transform we're going to have to explore. But before we do that, let's actually find a couple and take a look. Okay, so let's do this practice problem, and I will say right up front, I warned you this is going to be math intensive. So all we want to find, this looks innocent enough, is the first one, t times the unit function, the unit step function. Okay? And we can begin this. The integration is going to get a little messy because we're going to want eventually to use integration by parts. Right? So what we're after here is an f of s, which is equal to what? The integral from 0 to infinity of t e to the minus st dt, right? That's the definition. Okay, so we're going to have to do some pieces here because here we've got a product of two functions in t. Okay, so let me back up and refresh you. I'm not sure, maybe from Calc 2 or something like that, you did integration by parts. So let me just refresh some of that. We need to identify two functions that are going on here. So I'm just going to call them, I'm going to call two functions, f equals t. That's the function t. And the second one that I'm going to need is I'm actually going to need something that I'll call g, but it's going to be the derivative of g. I don't know if you remember that notation, but we'll use it anyway. That means the derivative. And I'm going to say the derivative of g is e to the minus st. Okay, now I'm looking downstream a little bit because these are the two parts right here. This product is what sits under here, right? This is f g prime. All right, maybe I should, so it's not divided by that. That is that. Okay, so what does this give me? This tells me then f prime is equal to dt, and g is equal to what? If I integrate this, it's going to be minus 1 over s e to the minus st. Okay, so now we've got our four things there, f and f prime, g and g prime. All right, and what we want to remember is that the integral, the differential of a product is what? The first times the derivative of the second plus the second times the derivative of the first. Okay, we got all that. So if we just go on here to integrate, if we integrate the left side, fg product dt, and then we integrate the right side. So the integral of f g prime dt plus the integral of f prime g dt. Okay, this left side, the integral of the differential of the pair, is just the product. Okay, so all we need to find out is what's going on the right side. So we do this. I'm just going to rewrite this in a neater fashion. So it's still our f g prime dt plus integral. I haven't done much here besides make that substitution. Dt. Okay, now what's going to be of interest? I need to recognize these two terms, integrals on the right. You know, I need something to look like this, right? That's what I'm going to be aiming for. And that's why I deliberately set up f to be t and g prime to be e to the minus st. So this integral looks like fg prime. So I want to, where am I at here? I want to solve for this right here. So this is going to be the integral of f g prime dt is equal to what? Fg, just the product, minus the integral of f prime g dt. Okay? So now we have the product of two terms, and that up here is going to be our t times g, right? So for us, this is going to amount to, maybe I'll head back up here then. So for us, this is going to amount to, here's our fg, so that'll be t times minus 1 over s e to the minus st. Okay? And this will, of course, evaluate between 0 and infinity, but that's all right. If we just look at this, by the way, at infinity, this term is going to be 0, and at 0, this term is going to be 0, right? So this whole thing is probably going to be 0. All right, but then we've got a second term going on here, which will be the integral of what? Now, f prime, which is just dt, right? So we could say 1 times dt, times g, which is minus 1 over s, e to the minus st, and then here's our, all right, between 0 and infinity, our one-sided guy. Okay? So now with that 0, where are we at here? This is, let's get it all together. We're going to have 1 minus. Here's another minus, so that makes it plus. And now when we do the integral of this, we're going to have yet another minus. So this is going to be what? Minus 1 over s squared. E to the minus st. And we can evaluate that between 0 and infinity. Okay? So, where does this leave us? I mean, the end of all this is a constant. Right? And what is this? At 0, this is 1. And at infinity, this is 0. So this is going to leave us with the lower limit minus a minus 1 over s squared. So we'll be left with 1 over s squared. Okay? That's the first one. But the idea that I wanted to get across there, I'm not going to drag through all of the others, right? But there are the other two with the a and b. They're simply looking at, where are they? Looking at now adding, instead of t, we're adding another function in front with the unit function behind, right? Same thing as we did here. We had this in front and the unit function behind. So you can see the math gets quite interesting. This is recalling old stuff, probably from Calculus 2 or somewhere along the line. I've forgotten where it was. But these are going to be the basic ideas if you're going to be deriving all of these particular, Laplace transforms. You will quickly become familiar with tables of transforms. All right. I want to go back, or not go back, I want to look forward to actually an example that's in here, which is, again, being monitored or being made into a one-sided transform by multiplying by u of t. But this is, what's the Laplace transform of a sine wave? And we're back right away with, having to make substitutions. We were back with having to do integration by parts. I mean, who remembers that? And now we're having to make substitutions because things are in at the exponential, I don't want to say domain, but in the exponential form of expressions. And so we need to recall a lot of substitutions here. This is one now. I sort of pointed out earlier when we left the inverse. There was that, e to the j omega t thing. Let me just put this in simple form. You may remember this one, cosine of x plus I sine of x, right? That's just a term I'm used to from, it's j now, but, here you have it. So if we do a couple of things, like if we express e to the ix, we could also express e to the minus ix, and that would be what? Cosine of minus x plus I sine of minus x. Got to be a little careful there, but let's recall, or draw the graph and figure it out if you want, that cosine of minus x is equal to cosine of x. And sine of minus x, is equal to minus the sine of x. Okay, so what is all this about? We're trying to isolate a sine term as a function of exponentials. And the book just, in this example, just sort of jumped right to it, as though everyone knew this right off the top of their head. I didn't when I read it, so I thought, I better think that through. So let me finish with that. E to the ix, right, minus e to the minus ix is equal to what? Cosine plus I sine of x minus, and I do this substitution, minus cosine of x. You see where this is headed. I'm going to be able to get rid of that cosine. But then I'm going to have minus a minus sine of x. So that's going to be plus I sine of x. Okay, all substitutions. So this is equal then to the cosine terms cancel, and I'm left with 2I sine of x, right? And if I divide both sides of this by 2I, I have e to the ix minus e to the minus ix over 2I is equal to the sine of x. I'm so used to from the past, I apologize for not using omega t, which is what's up here, but I'm so used to using simple terms and substitutions and doing this stuff in terms of x's, and occasionally you'll see me throw in u's and some other alphabet letters that I've seen in my past. So Forgive me, but you get the idea. We end up here. We can easily substitute in terms of our upstairs problem, right? We've got the sine of omega t is equal to e j omega t. I'll go all the way and plug that in, minus e to the minus j omega t over 2j omega t. All right, and not omega t. This is not there. All right, and so this gets the point, the important substitution to be made, just like we had a substitution to make in practice problem 1. This is often the case around Laplace. So you can follow the rest in the text. Once you've got this substitution in hand, making the Laplace, here's that piece that needed to happen. After that, it's just factoring out the 1 over 2j and then doing the integrations, right? Where you just put together each of these omega t terms with this, right? And you then have a more complex exponential coefficient, the plus and minus j omega, s plus j omega and minus j omega. But this we can handle because that is now just, right, some, call it e to the minus at, right? And we know how to integrate that, dt. So it's just, in this case, 1 over, right, you have the minus and the 1 over the a, in this case s plus j omega, but it's minus a, so it's 1 over minus a, so 1 over minus the quantity s plus j omega, and here we have that, and and then you just put this together by what, reducing the denominator, so cross multiplying, and you get this nice term, right? This would be s plus j omega, whoops, right, minus s minus j omega all over the product s squared plus j squared, whoops, minus j squared omega squared, and a minus j omega turns this into a plus. So we have our denominator, and in the numerator we've got s minus s, and then we've got, oh wait, I wasn't careful here. It's s plus j omega minus minus s minus j omega minus a minus j omega, so this should have been a plus. Right, so it's 1 over 2j times 2j omega over s squared plus omega squared. And of course those disappear and you get exactly what the text got, no surprise. But a lot of substitutions and a lot of careful math. So you're probably going to see that a lot. You see it in this problem where they give a nice tidy solution, but buried in it is an awful lot of math, especially around substitutions. This is going to happen with Laplace. So next we're going to move on to properties and cover just the first few. There are going to be quite a few of them. So we'll go with the properties, and there are quite a few of them. I'm going to list them all first, and we'll tackle about half of them to close out this lecture, and then finish them in the next. All right, so the first is linearity. We want to know that things are you know, if I multiply by constants or if I add two transforms by multiplied by constants, they will in fact add. Scaling is the next one, and this will be, a frequency scaling where we'll discuss that. But the idea of these is if you find one form of the transform, simply by applying one of these properties, you can quickly arrive at another version of the transform that fits your case. Often, all we need to do is multiply the frequency. That's the scaling attribute. Okay, we're going to do shifting, and we do this in both time and frequency. So it's a common property, but it will occur in both forms. We're going to look at time, and in the time domain, we're going to look at three different things: differentiation, integration, and periodicity. Okay, so we'll spend a little time on these, obviously. We'll go back to frequency and look at frequency differentiation, and then we'll also look at initial and final values. Okay, so this isn't quite the order that they'll be in, but it does start out that way. So here's linearity. All right, so linearity is the first of these. And if we think back to, oh goodness, I think times when maybe we were talking early in algebra, maybe even in high school, things like associativity and commutativity and that kind of stuff. This might fall into that category where I've got, if I want to add two functions, the Laplace of two functions, I can do that. And the constants, A1 and A2, are constants here. All I need to do is add the constant times the individual Laplace transforms to get the new Laplace transforms. Okay, it's linear, and you can do that. All right, so as an example, the Laplace of the cosine of omega t and the unity of the step function tells us this. We're looking at the Laplace. I'm making the substitution now inside the cosine omega t. So I'm just substituting cosine omega t is e to the j omega t plus e to the minus j omega t. All right, that being the case, linearity tells me I can break it into two functions where a1 and a2 are a half, and I get 1/2 the Laplace transform of each of the exponentials. Okay? And that we know because we've done the exponentials, we've done the Laplace of those, is just 1 over s minus j omega and 1 over s plus j omega. Okay? Been through that a bunch. We just got done doing this, as a matter of fact, this exact reduction here. And it's s over s squared plus omega squared, right? We cross multiply and clean everything up. All right. Scaling is the next. In scaling, you can see what we want to do is say, if time is multiplied by some constant, once again, a is a constant, the integral of that Laplace, or the function of the Laplace, would be the function of at. E to the st remains the same, no change here, times dt. All right? And we can express this as, with a substitution of x, right? We can replace at by x. So we make the substitution. This is important. X is equal to at, right? And we go on to say dx is equal to what? dt. All right, so we're going to make those substitutions through here. This is like dt is equal to dx over a. Okay, so that's what's going on over here. That substitution gets made for dt. And then what? In t, we solve this as t is equal to x over a. All right, we can do that and make that substitution. So that's what gets us to this point. The rest is just doing the math. So we factor out 1 over a, factor that out here, do the integral, and the integral is f of x e to the minus x s over a dx. But we know what e to the minus x is, right? And so with this substitution, what we're saying is we now have the Laplace of a scaled function, where the time is scaled, is equal to 1 over a times the original transform. Remember, this is a transform. Laplace, CE, not SE. So the time-scaled Laplace transform also scales both s by dividing them down. It scales both s by dividing it down, and the magnitude by dividing it down. All right? As an example, we did this. We just got done doing this. We just got done doing it almost this right up above. The Laplace of the sine of omega t is omega over s squared plus omega squared. We did this earlier in this lecture. All right? This scaling would say if we simply wanted to, find the Laplace of 2 omega t, a equals 2. So here it is, 1 over a, s over a. Simple substitution, and you've done a scaling. Nice. All right, we want to talk about a couple of shifting things, both characteristics or properties, both in time and frequency. Time is probably the first one that maybe the one that makes the most sense to us most readily. So here we have, you can see the Laplace. If this were the Laplace of f of t, right? Now we've just shifted t. Now which way have we shifted it here? By saying t minus a, we've actually shifted it to the right, right? Because for the unit step function to turn on, we must wait a time units. So it's going to wait in the positive direction. We're, by the way, looking for a to be a positive number. Now, if we want to make the Laplace of this, and we go through the math, we're taking the integral of f of t minus a times the unit step of t minus a, and of course e to the st dt, again, for positive a. All right, how does this move forward? Basically, it says, we know this thing goes from 0 to 1 at time a. So that's either off and zeros everything, or it's on and is a unity multiplier of everything. So what that really did was move our lower bound, or our lower value in the boundaries of the integration. Okay? So this can be, if we make the substitution, what's the substitution that's obvious here? The substitution is x equals, you notice we're back to this substitution stuff again. Going to be pretty common, constantly recurring in the whole Laplace business. So if we say x is t minus a, right? So here's that. And now if x is t minus a, then t is equal to x plus a. And here's that going on, right? That going on. So there's just that substitution going on where t, x is a translated t. So if we do this now, this math becomes kind of straightforward. We've got a function of x, which we're going to pull out with this. Because this is the sum of exponents, we can separate this obviously as the product of two exponents, right? E to the minus sx times e to the minus sa. So we've done that here, but e to the minus sa is a constant. And so we're left with fx e to the minus sx. But we recognize this whole thing as the Laplace of s in the first place. Okay, so apparently all that happened for time shifting was we ended up changing the Laplace by multiplying by e to the minus as. How does this matter? Here it is summarized in black, so like it gathers it all together. How does this matter? Okay, we've just gotten done doing cosine, the Laplace of cosine omega t. If we want to shift it, right, if we want this, whoops, where are we here? If we want this, the shifted times, all we do is take the old and multiply it by this, okay? And that gives us our time-shifted cosine. So what does that look like? I mean, what we're really talking about is this. This was the original, right? And this is now where we're moving it, right? Where this distance is a, right, on a time axis here. Okay? Let's look at frequency shifting. Frequency shifting now, a similar process mathematically. So we want the, we don't have a unit step function of t minus a. We didn't do a time shift, and the function remains a function of time. Instead, we do the frequency shift by multiplying by an exponent, all right? And that looks like this as a Laplace, right? All this is just taking the Laplace of this original function here, right? The Laplace of this. And so we're just writing it always back to the original math, right? We're just plugging in this new piece here into what we've always been doing for Laplace, okay? And if we expand that out, right, we've got this, whoops, we've got our f of t, and now we add minus at, so it's s plus a times t. Here is that. And this all looks like what? F of t e to the minus s plus a times t. Well, that's just the Laplace, right? Since this is the s domain, that's just the Laplace. Oh, and doesn't this even look like a frequency shift? In the same way the unit step function shows a time shift, this looks like a frequency shift. Behaves just the same way. Okay? So the Laplace of a frequency shifted waveform is just the Laplace of s plus a. So we've constantly been working with these two. We've done problems with them and so forth. What are they going to look like, right? The Laplace of a frequency shifted cosine, right? There it is. You just go into every one of the s's and plug in s plus a. Even though it's squared, fine. Same thing is true for the sine wave. Okay? So I think we'll quit here for this lecture and pick up with more properties. There are time, as I did in that original list, there are several properties for time: differentiation, integration, periodicity. We got to do initial values, and we got to do frequency differentiation. We'll pick up all those next time, and then do problems to illustrate them.